Okay, we're going to continue on here. We got into electrochemistry last time. Which is really about redox reactions. And as we talked about, redox basically is our oxidation reduction reactions. And we talked about a few different sort of definitions of each of these things. The ones, again, that we use mostly here in general chemistry is really more the electron definition, where oxidation, we lose electrons, reduction, we gain electrons. But we also talked about a few other definitions. Oxidation also can mean that something gained oxygen as it goes from reactants to products. It could also mean that it lost some hydrogen as well as it goes from reactants to products. Reduction is sort of the opposite there. It means that it will lose oxygen as it goes from reactants to products. It will gain hydrogen as it goes from reactants to products. More so in organic chemistry there, you oftentimes will look at those sort of definitions for oxidation reduction. But a lot of times we will look at more the electron definition, but occasionally it does sort of pop up. The other thing we sort of talked about as well is a couple of things, which is our oxidizing agent. And our oxidizing agent, again, is the substance that gets reduced. And because it gets reduced, it's going to gain electrons, which means it's got to cause somebody else to lose electrons and go through oxidation. And we also have the reducing agent. And that is typically the substance that gets oxidized. And it's, again, sort of the opposite reason there. Because the substance gets oxidized, it will lose electrons. Which means somebody else will gain electrons and obviously be reduced. Hence, it is causing the reduction in something else. Remember that they always occur together. So if something is being oxidized, something else should be reduced along the way. We can also write half reactions. And in the oxidation half reaction, remember that electrons should end up on the product side there as they are being given off. While the reduction half reaction, the electrons should be on the reactant side as they're being gained. One of the essential things of sort of balancing redox reaction, especially sort of basic ones as well, is you always want to make sure that you have the same number of electrons in each half reaction before you add them back together. So it may require in some cases that you may have to multiply one of the half reactions or both of the half reactions by a common number to get the same number of electrons. They should always cancel out because the idea here is however many electrons somebody loses should be the exact same number of electrons somebody gains. So there should be a sort of an equal transfer of electrons. We can identify oxidation reduction by looking at the oxidation number that we talked about, or state. And the oxidation number of state, as we talked about, again, is not always the sort of charge that we envision on a lot of elements, especially when they're in ionic compounds, but it is sort of the charge that they would take on in whatever sort of system they're in. So a lot of times we do come across a lot of elements that are covalently bonded, which means they're sharing electrons. So based on what they are covalently bonded to and the electronegativity of everybody involved, again, some things that we normally think of as having a negative sort of charge, in that instance, when they're sharing electrons, can take on more of a positive oxidation state. So again, something like chlorine is very commonly more of a positive oxidation state in a covalently compound, or covalent compound, obviously, than the negative one that we associate in a ionic compound. Remember that oxygen is usually a pretty good place to start. It's -2. Then, you kind of distribute the oxidation numbers to everybody else. You want to make sure that your oxidation numbers adds up to the charge if it does have a charge overall, or it adds up to 0 if it's a neutral sort of molecule. The only time oxygen is not -2 is, again, if it's peroxide, which means it would be -1 in that particular case. We also can use a basic number line if you're not sure who is being oxidized or reduced. And again, if you see their oxidation state move towards the positive direction, then that guy is going through oxidation. If you follow the oxidation state from reactants to product and it's sort of moving this way on the number line, That's becoming more negative, which means it's going through reduction. So that's a super simple way to figure out oxidation and reduction. Just draw an arrow and see which way it's going. We finished up talking about balancing reactions in both acidic and basic conditions, a little bit more difficult than just a simple redox reaction where you balance out the electrons. So here the basic steps are really to split into the half reactions. We want to balance all elements except oxygen and hydrogen. We then will balance oxygen by adding water to one side that needs the oxygen. And again, remember that every time we add water, we are oxidizing 2 hydrogen. So to the other side, we need to add 2 H pluses for every water that we put in there. Then you want to balance out the charge on both sides by adding electrons. And then you want to make sure same number of electrons in each half reaction. And then you could add it back together. And that would technically give you your equation balanced in acidic conditions. Remember, if we're going to do basic conditions, you pretty much do all the same steps. The only thing at the end there is we add OH minus to both sides equal to the H plus. So if you want basic, you follow all those same steps, then you add OH minus to both sides equal to the number of H pluses you have. You combine some waters, and then you reduce down some waters, and then you will be balanced in basic solution. Any questions on any of those steps there? All right, so why don't you try one since I did one last time, just make sure again, you know how to do these things properly. So let's take a look at ones here, which may be the next one that you got, I think. All right, so why don't you do this one here, balance this guy in basic conditions, see what you come up with. Also identify what's being oxidized, what's being reduced, and also the oxidizing agent and reducing agent as well. Okay, let's take a look, see how you're doing. So we got our reaction here. We want to balance it in basic conditions. Sometimes it's a good idea to get an idea of obviously what is going on in terms of oxidation and reduction. So if we assign some oxidation numbers here, this guy's going to be -1. Our oxygen here will be -2. There's 4 of them, which means it's -8. And there's an overall -1, which means the Mn in this case is +7. I2 is in its natural state, uncombined, which means it has an oxidation number of 0. And coming over here to our last guy, again, assigning -2 there to the oxygen, that's going to be -4. And there's no overall charge, which means to balance it out there, the Mn would be a +4 oxidation state. Once again, if you're not sure, you can use the little number line approach. Iodine is starting at -1, which is over here, and it's ending at 0, which means it's actually moving in a positive direction. And that means that the I- is going through oxidation. And once you identify one thing, you pretty much know the other guy here is going through reduction by default, but you can verify it by doing the same thing. For the Mn, it's starting at +7, which is like here, and it's ending at +4, which is moving in that negative direction, which means it is going through reduction in this case. That also means that our reducing agent in this case would be the I-, and really the Mn +7 is our oxidizing agent, or this particular substance here. Any questions on how to identify all those things? Once we have it identified, and again, it's good to know oxidation reduction because it will help us make sure later on when we're balancing this thing, that we do put things in the right spot. We're going to break it off into its half reactions, and you simply just take the elements that are the same on both sides. So we have an I minus that goes to an I2, and we have a MnO4 minus that goes to an MnO2. And once again, that is our reduction. No, that is our oxidation here. Our oxidation half reaction and our reduction half reaction, just to remember that as we go through it. Once we have it split off, the next thing that we want to do really is just balance it like a normal equation, everything other than oxygen and hydrogen. And in this case, we do need to put a 2 there to balance out the iodine. On the bottom, we basically have one Mn on both sides, so we don't have to worry about that. Now that we've done that, the next thing we want to do is balance out oxygens, and we're going to add water. So the top guy has no oxygen, so we don't have to worry about it. Bottom guy on the left there has 4 oxygens, on the right has 2, which means on the right hand side we do need 2 waters to balance out the oxygen. That also means that to the left hand side in this case, we will need to put 4 H pluses to balance out the hydrogens there, so that we're all good. Any questions so far? At this point, we're ready to balance out the overall charge now that we got everybody balanced. Also a reminder that if ever in a half reaction you're starting with more hydrogens on one side than the other, you can simply just put H plus on the other side to balance it out up front, and that will all work. Overall charge is the best way to do it. We got a -2 action happening there. Overall here is 0, which means a couple of electrons would be needed on the right-hand side here to give us basically a -2 on both sides. We have basically a +4 there. This entire thing adds up to a -1. That gives us a +3 happening over there. And in this case, we do need 3 electrons, as this is 0 and this is 0. So the 3 electrons should go over here. I'll squeeze it in right there, maybe 3 electrons will be squeezed in. That gives us a -3 on both sides at this point. I'm sorry, it gives us actually a 0 on both sides, as those guys then add up to 0 and 0 at that point. Any questions on that? Again, sometimes people are taught to go element by element and see, how many electrons each element sort of lost. The best way to do it's overall charge on both sides, because frankly, the overall charge in each of these things basically does the math for you. So why reinvent the wheel if it tells you already what the total is going to be? All right, now that we have our electrons added, we do want to add them back together, but we can't do that until we have the same number of electrons on each half reaction. And by the way, we could perhaps verify that we've been doing something right here. The electrons ended up on the product side in our oxidation half reaction, which is good. Electrons ended up on the reactant side in our reduction half reaction, which is where they should end up. Remember, never to the same side, right? When you add them, they do need to cancel out. So common number between 3 and 2 is 6. So I'm going to multiply the top guy by 3, the bottom reaction by 2. And if we do that, top reaction gives us 6I minus, goes to 3I2 plus 6 electrons. Bottom one there goes 6 electrons plus 8 H pluses plus 2 of the MnO4 minuses, goes to 2 of the MnO2 and 4 waters. At this point, we can now add these guys back together. Once again, the electrons should always cancel out. Anything that's the same on opposite sides of the arrow can either completely cancel out or reduce down. And I think in this particular case, that is it. So everybody on the left-hand side is going to stay there. So we have 8 H pluses plus 2 MnO4 minus plus 6 iodide. To the other side, 3I2 plus 2 MnO2 plus 4 waters. Now, technically speaking, if I wanted to just balance it in acidic conditions, I'm done. And we know it's acidic conditions because there's H plus there at the end in the actual equation. Should be balanced. Just really quick looking at it, we have 8 hydrogens on the left, 8 on the right, 2 Mns on the left, 2 on the right. We have 8 oxygens on the left, 4 and 4 on the right. There's 8, 6 iodides. Overall charge on the left-hand side is +8, and -2 is +6, and -6 is 0. Overall charge on the right is 0. So again, they do need to be balanced both ways, like a normal equation, same number of elements on each side, and also overall charge needs to be the same. Since we are doing basic in this case, this is probably the best move is just to do the acidic conditions. Now we can turn it into basic by taking an equal number of OH minuses to each side as we have H pluses. So in this case, we will add 8 OH minuses to both sides here. This side here will combine to make 8 waters, which we usually could reduce down now. So there's 4 waters on that side. That would then reduce down to 4 waters and 2 of the MnO4 minus and 6 iodide, 3 of the I2 plus 2 MnO2 and 8 OH minuses. And this then should be a balanced in basic conditions. It's basic because we see OH minus in the equation, not H plus like we did above. Once again, it should still be balanced. So 8 hydrogens on the left there, 8 on the right. We have 4 oxygens and 8 is 12 oxygens on the left. 4 and 8 is 12 on the right, and 2 MNs and 6 iodines on both sides. Overall charge here on the left is going to be 0, -2, -6, which is -8. Overall charge here, 0, 0, and -8. So we are balanced again, both in charge and in elements there. Any questions on this here? All right, we've done these before, yes. Everybody feels good? All right, then we will continue on to the main topic. Just want to make sure, again, everybody's hopefully on the same page on how to do these. All right, then let's continue to talk here about, and in case you want a couple more to practice, there's a couple more examples there in the notes if you like. Let's then talk about really the main part of this chapter, which is galvanic cells. And galvanic cells are really just redox reactions that occur. And in a galvanic cell, this is typically how you could build a galvanic cell in the laboratory. A couple of beakers, we have usually some type of solid electrode on both sides. In the solution is typically a solution that has the same ion version of what's on the solid electrode. So whatever the electrode is, usually you have that ion flowing around in the solution. So for example, here's zinc, and here we have zinc ions flowing around. That's copper, and we got some copper ions floating around in the solution. So there are 2 parts, kind of a few more than 2 parts, but 2 main parts to a galvanic cell. There's the anode side, and on the anode side, that is where oxidation occurs. So that is where they lose electrons. So as they lose electrons, just in case you're not sure, when something loses an electron, for example, goes from the solid state, then goes for a swim, basically. And things with charges are typically found in the solution part, right? So that's where they end up. Those electrons that are lost takes a trip across the wire here, gives you some voltage, and goes down to the other side of the galvanic cell where we have the cathode side, and that is where reduction takes place. So those electrons that come in basically then kind of hook up with the guys in the solution, and those guys gain the electrons, which means they actually go from a charge to no charge, and they go for a jump out of the solution basically into sort of the solid phase. You can sometimes see them coating onto the solid electrodes if you run these cells and stuff like that. So this process continues. It gives us usually positive voltage. Here's our half reaction that's happening on here for our zinc. Our zinc is starting at 0 oxidation state, ending at +2, becoming more positive and going through oxidation. On the other side, our copper starting with a +2 oxidation state, ending with a 0 oxidation state, gaining those electrons and becoming negative. The overall reaction when we add these together is what we see down here, our zinc with no charge going to our zinc with the +2 charge by losing those electrons, the copper with the +2 charge gaining those 2 electrons, and ending with no charge or oxidation state is really a better way of saying that. A really important part of this is there is sort of a potential difference between sort of the anode side and the cathode side. Electrons are negatively charged, so kind of like a bigger sort of positive side on that side of the cell. That's going to draw those electrons right coming to the other side. A really important part that kind of keeps everything flowing is the salt bridge. The salt bridge basically will connect both of the beakers in this situation. The salt bridge is usually filled with some type of electrolyte solution, some type of salt like potassium chloride. And what happens is, in this example with potassium chloride, the chloride ions go down this way, and the potassium ions basically go down this way. So it does play an essential role, the salt bridge, to keep everything flowing correctly, because what would happen if I took the salt bridge out? We wouldn't want to necessarily do that, because what's really happened if we just look at, say, a galvanic cell, and this is our anode side, this is our cathode side, and let's just say we did pull the salt bridge out of it. We can see exactly what's happening here, right? As this guy goes through oxidation, everybody's going for a swim, right? Which means they're going to be making positive ions, right? It's going to build up on this side. Electrons will go to the other side, and those electrons over here, when these guys basically jump out of solution, those electrons are going to end up over here. Problem is, at some point, if you took the salt bridge out, you have these negatively charged electrons that want to go this way. But what happens when it encounters this big old positive charge you just built up here? They're not going to go, right? They're going to be more attracted to stay on this side. And that is really the function of the salt bridge, is to prevent really the buildup of the wrong charge on the wrong side. And that's why we see here the negative ion goes into the sort of positive side there to sort of neutralize that buildup of positive charge that you would get if it wasn't there. We also see a positive guy kind of build up here to sort of neutralize some of that negative charge that would build up as well, because when those positive ions go out of solution, your other spectator ion, which is negative, right, will start to build up a negative charge on that side. So that positive ion goes in there to sort of balance it out. It keeps the proper sort of balance on both sides that allow the electrons to go from one side to the next. So the salt bridge really works to minimize the wrong buildup on each side of your galvanic cell, which would, if you got rid of the salt bridge, essentially draw your cell to a stop. Basically, you really want to get the electrons going from one side to the next. So by the negative guy going to our anode, the positive ion going to our cathode, it keeps those charges where they should be, allows the electrons to, again, freely flow from one side to the next, which is ultimately what you're looking for. Any questions on what the salt bridge actually does? Yeah. By the way, if we pulled the salt bridge, right, and we were looking at voltage, what should probably happen to the voltage? It would go down, right? And again, we wouldn't have those electrons going to the other side. It would stay on the anode side, and obviously we wouldn't have much of a voltage that would happen. Any questions on the galvanic cell there? Okay. So as I mentioned, there is that sort of potential difference that occurs between sort of the anode side of the cell and the cathode side of the cell. And that is sometimes referred to as the cell voltage. A volt is basically a joule of work per coulomb of charge transferred. Coulomb's a unit of electrical charge. So 1 volt is equal to a joule over a coulomb. That's a conversion that we will kind of use a little bit later on as well in some of the calculations. It's sometimes also referred to as the electromotive force, or the EMF of the cell, or the cell potential. So sometimes in problems, they ask you to solve for any one of those 3 things. Solve for the cell voltage, solve for the EMF of the cell, or solve for the cell potential. Essentially, it's all the cell voltage is what you're calculating, basically, when you're asked to solve for any of those things. If we look at this cell there, you can hardly see it, but the salt bridge is right about there. And again, this is our copper cell. We could hook it up to a voltage meter there. And again, usually positive voltage is pretty good here. This again is our 0 going to +2 oxidation anode side, and our +2 going to 0 reduction, our cathode side. Now, we can write sort of a shortcut to the reaction, which is sometimes referred to as the cell diagram, and that is what this is down here. So we basically start kind of like the galvanic cell is. The anode goes first, followed to the cathode. So the way this typically is sort of put together is reactant product is typically how you could kind of go from the cell diagram back to the reaction. Again, you can see reactant and product, reactant and product. So that is again how you can kind of go backwards. So this is really our anode sort of compartment, our reactant and our product that's going to be coming out. And then we have these two lines here. This represents the salt bridge. And then we have our cathode compartment, our copper ions floating around in solution, and our copper solid here that's going to be made. Sometimes, as you can see here, people will put in the concentrations. Sometimes they may even put pressure. You may see some other things in here, like a gas, and maybe something like platinum or something like that, which is sometimes used when there is not a physical electrode. So sometimes if you have an electrode that's a gas, you can obviously have a physical version of a gas. So sometimes they'll use something like graphite, they'll use something like platinum or something like that, that is sort of the solid version of that gas that's used as an electrode. So sometimes you'll see that in your cell diagram. Remember that these are pretty much standard conditions here. That is 1 atmosphere, 1 molar, right? 25 degrees Celsius. So this is basically running the cell under standard conditions, which is 1 molar for each of these concentrations. Any questions on that there? So let's talk about a really important thing when we're talking about galvanic cells, and that is what is sometimes referred to as standard reduction potential. It is sometimes referred to as SRP, which stands for standard reduction potential. There is an entire table, an SRP table of standard reduction potentials. And as you might imagine, and as we will see that table, they are all written as reduction reactions, hence the standard reduction potential as what it is referred to. So if we hook up this sort of cell here where our zinc is our anode, and in this case, hydrogen is actually our cathode. And as I was mentioning just a second ago, here we are actually using platinum as the sort of physical electrode for hydrogen. Hydrogen obviously being sent in there at 1 atmosphere, which is standard pressure, which is why that is there. Here is our cell diagram. Once again, this is our anode compartment there, and this is our cathode compartment. And because there is a gas, they do include the platinum in there, even though it's not really part of the overall reaction, just to show that is what they're using as the physical electrode, but really it's the hydrogen to the H2. The anode here being our zinc going from 0 to +2, losing electrons. And it is our hydrogen here at +1 to 0 that is gaining electrons and being reduced, and that gives you your overall reaction. Once again, just to show you that you could go from the cell diagram to the equation. That is the reactant, that is the product, that is a reactant, and that is a product. And again, that is how it relates from cell diagram to equation. Clear, as I just mentioned, we don't put the platinum in there as it's not really part of the reaction that's going on here. Now, if we hook this up and we actually measure the cell voltage, we can measure the standard reduction potential, which is sometimes abbreviated E with a naught. And it is the voltage that's associated with a reduction reaction at an electrode when the solutes are at 1 molar and 1 atmosphere basically standard conditions. Now, oftentimes in chemistry, right, if we need something to use as a standard, sometimes they just pick something. And for SRP values, they basically pick the hydrogen electrode, which is sometimes referred to as the SHE, for standard hydrogen electrode. And they basically just arbitrarily gave it a value of 0 volts. So that sort of reduction reaction for hydrogen is really the standard at which they sort of compared everybody to. Basically what they did is they took the hydrogen electrode and hooked it up with everybody else, and then got the voltage and did some math here to basically figure out what the standard reduction potential is of everybody. So again, when we look at this table in a bit, we will see that they're all written as reduction reactions, and this is the SRP value that goes for that. When we do see an SRP value for a particular reaction, it's specific for exactly how it's written as a reduction potential, and that is the value that we will use or see when we look at the reaction. So if they did this, for example, and hooked it up, the zinc and our hydrogen electrode, they will get a cell voltage of 0.76 volts. So using this equation, which is a good equation, but you should be careful with this equation. I'm going to explain it to you right now, and it might not make sense right at this moment, but hopefully in a bit here, it will make sense. To figure out the cell voltage in a galvanic cell, you could take the E of the cathode minus E of the anode, which means you basically could look up SRP values in the table. And you could put it right into this equation, and you could get the E of the cell. So they used this equation and the cell voltage that they got when they did this, and they were able to deduce that the zinc reduction reaction here has a voltage of minus 0.76 volts. Now, when we go to the table and we look up these values, frankly speaking, one of the values that you look up are going to be incorrect. And that is because basically what's happening here in a galvanic cell is a redox reaction, which means one of the reactions should be an oxidation reaction and the other one should be a reduction reaction. But when you go to the table, they're all written as reduction reactions, which means technically speaking, you should reverse one of the reactions. You should kind of turn it around the other way. And when you turn it around the other way, as we'll talk about, what that does to the SRP value is it changes the sign. So let's just say, for example, here we had a reaction, and in this particular case here, it is actually the anode in this case, which means this reaction that we're looking at here, which is what you could find in an SRP value table, is really the zinc reaction in the reduction sort of situation that's going on. In this actual equation, though, it is not really going through reduction. It is actually going through oxidation, basically. So if we wanted to write the correct reaction for the oxidation of zinc, we actually would just flip this reaction around. It would be zinc going to zinc 2+ and a couple of electrons. And that actually would be the oxidation reaction, right? That is actually going on actually in this example versus the reduction reaction that we would find in the table. Now, how that affects the E value is the E value for this reaction actually is positive 0.76 volts. So this equation up here, where we take the cathode minus the anode, is a perfectly good equation. Personally, it's the equation I use a lot of the time. And the deal with that equation is, even though technically speaking, one of the values that you find in that table is technically incorrect because it is a oxidation reaction rather than a reduction reaction, you should take the values exactly how you find them in the table with the whatever sign it is, because that is why the negative is here, right? So technically speaking, we would need to change the sign that we find in the table. And if we leave it as negative, negative, and negative, we'll turn it into a positive value, which is what it should be. So if you use this equation, E of the cathode minus E of the anode, you should never change the sign for one of them in the table. You should just take it from the table, whatever sign it is, stick it in there. If you want to really do it technically correct and have all the technically correct values, you should change the sign. And then if you change the sign, you should actually add them together and not subtract. So you should use this equation if you do not change the sign of the anode, or if you want to change the sign of the anode, you then should do something like E of the cell is equal to E of the cathode plus E of the anode. You should basically add them together. So I would highly recommend, and again, it may not make perfect sense yet until we do an example or so, but I would highly recommend you choose one way and stick with it and not kind of flop back and forth. Otherwise, you'll probably find yourself switching signs when you shouldn't, and you'll end up with the wrong sign. So I personally usually use cathode minus anode. That way I can just go to the table, not to worry about changing signs, and just grab the numbers I need, put it in there. And that subtraction there will change the sign for you. But again, if you want to do it yourself, you can change the sign and then add them together. Any questions on that? Now, it is important, though, that if you did have a half reaction and you want to give the E value, you should give the correct E value. So if you wrote this reaction here, the E value really should be a positive value. Or if you wrote this reaction here, the E value should be a negative value. So it does specifically for how it is written. All right, so let's take a look at a couple more of these. So they hooked up the hydrogen electrode here with copper and ran it, and they got a cell voltage of 0.34. In this case, we see that the hydrogen electrode is actually the anode, and in this case, the copper is the cathode. This demonstrates also another important thing about galvanic cells. Pretty much anything can be an anode or a cathode. It may just work or not work. By the way, if you put something together and it doesn't work, which means basically you get negative voltage, how do you fix that? You just switch them. Yeah, so you switch the anode and the cathode around, and then you get positive voltage, and it will work. Kind of like when you put your battery in backwards. Doesn't work, right? You flip it around the right way, it works. Battery is pretty much a galvanic cell kind of happening in a closed compartment. So in this particular case, our SRP value here for copper reduction is 0.34. And again, here overall, we have our hydrogen going from 0 to +1, which is being oxidized in this case. Our copper going from +2 to 0, which is being reduced in this particular case. So here is a table. You have a similar one in your book, and clearly you should memorize all these numbers. But if you look through all these, they basically are, again, all written as standard reduction potential. And the values are for there on the table. You also want to make sure that when you do go to a table like this, that you really do find the correct thing. There's sometimes things with different charges, like, copper 2 goes to copper 1 rather than copper 2 goes to copper with no charge. So you want to make sure you look at the entire half reaction before you grab a number, that you are grabbing it correctly. So let's talk about some of the things out of this table here, which is another version of it, which, yeah, you can't see that, but he's not really important, the numbers at this point. But a couple of things, the E, as I mentioned, is written for the reaction, just how it's written. So again, they will all be reduction potentials coming out of here. The more positive E, the greater the tendency for the substance to be reduced. So this is how you know when you are not given any information about your galvanic cell other than you put a galvanic cell together with these two things. This is how you can determine what should be your anode and what should be your cathode. The thing that gets reduced is your anode or cathode. The thing that gets reduced is your cathode, yes? So when you want to put a galvanic cell together and you look up the E values here in the table, the SRP value for the one that is more positive should be your cathode. The other guys should be your anode. Now, there is a very important part of that, which is if they actually give you the reaction, you should look at it and see what is being oxidized, what is being reduced, and you should go by that. Or if they tell you in words like, hey, this is reacting with this, then you should follow that. But if you're really not given any indication about how the reaction is taking place, other than you built a galvanic cell with these two things, then you could go to the table, and the one that's more positive should be your cathode, the other one should be your anode. But don't overlook, which is a very common mistake people make. They are given a reaction and they just go by the positive one all the time. You do need to look at the reaction if you're given to it and figure out who's being oxidized and who's being reduced. The half reactions are reversible, like I just did, and you can reverse it. When you do reverse the half reaction, basically it becomes an oxidation half reaction, and you would reverse the E value sign. So if it was positive, become negative, if it was negative, become positive. Sometimes referred to as a SOP, standard oxidation potential, yes, instead of standard reduction potential when you flip it around. The sign of E changes when you reverse it, and the other kind of different thing is, as we know, when we put these sort of half reactions together, sometimes we do need to multiply a half reaction by a common number to get the electrons the same. You can multiply by as many numbers as you want. It will not affect the SRP value. So you do not multiply the SRP value. The difference in like delta H, delta S, and all those things where you multiply all the way across. You don't touch the E value in this case, even if you have to change it for the electrons. All right, so why don't we try one here? I think you got that. What is the standard EMF or voltage of this cell? And why don't you also, doesn't ask it, but why don't we also write the balanced equation? Yeah. So write the balanced reaction or equation, and also what is the cell voltage here? Yeah. So what is the voltage? These are obviously S. Okay, let's take a look. So first off, we are building basically a galvanic cell out of these two things. We would go to our SRP table there and find these reactions if we didn't have them. And obviously our values there for the SRP, there are standard potential values. Here, we want to figure out in this case, which one is our cathode, which one is our anode. In this case, which one should be our cathode? Cathode should be the one that is more positive, which they are both negative, which means this guy here should be the most positive there. And that means that this guy would be our anode in this particular case. Any questions on that there? So since I asked you to also write the balanced overall equation that's going on here, that means technically speaking, we should reverse this reaction. That means really we would have something like this going this way and this way. And now that I reverse that reaction, my E value for this reaction technically should be positive 0.74 volts as I flipped it around. I do want to add it together, so taking out the middle reaction there. I cannot add these together yet because we do have different numbers of electrons, so I do need to multiply the top one by 3. I do need to multiply my flipped around one there by 2. And if I do that, that will give me 3 of the cadmium plus 2 of the electrons, or 6 of the electrons if I multiplied it there, 3 of the cadmiums. And in terms of my E value here, again, it is not affected by multiplying by that number, so it still stays the same. Multiplying the 2 on the bottom there, 2 of the chromiums, go to 2 of the chromium 3s and our 6 electrons. And once again here, my E value will not change. Now I could add these back together. And again, if I did it correctly, we should get rid of those electrons. Gives us the overall balance equation of 3 of the cadmiums plus 2 of the chromiums. Go to 3 of the cadmiums that are solid plus 2 of the chromiums that are aqueous. First off, any question on the overall reaction or how to get there? So now we also want to calculate really E of the cell here, and we do have 2 ways that we could do it. In this particular case, what I just did was change the sign of my anode from the table, which means if I wanted to do so, I could actually just add those together because I changed the sign. That would be minus 0.4 volts plus a 0.74 volts, going to get us, not that, it's going to give us minus 0.4 plus 0.74. There you go. Going to give us 0.34 volts in this case. Now, the other way you could do it, if you were really just doing this problem without the adding the equations together or anything like that, is you could use the other equation just to show you what I was talking about earlier. E of the cell equals E of the cathode minus E of the anode. In this case, we would not change the sign because we're going to subtract it. That's the purpose of the subtracting, is to really change the sign for us. So if we did that, we could just go in with, again, just the values that we find from the table without changing any signs, minus 0.74 volts. Again, that minus is going to change the sign for us, and we get obviously our positive 3.34 volts in this case. So this is what I was talking about earlier. It is really up to you, whichever way you want to do it. Again, pick one way to do it and probably stay with it. If you want to subtract, then just take it, don't change signs. If you want to change signs, then you should add in terms of the cell voltage. Any questions on that there? Again, don't do both. Don't change the sign and then like subtract or something like that to change it back. All right, any questions on that one? Yeah. Yeah, it doesn't, it will have no effect on it. Yeah. So unlike most things that we've done previously, like delta H's, delta S's, delta G's, where you actually do multiply by that, the SRP value is unaffected by multiplying by that coefficient. Yep. Other questions? Okay. So let's take a look at another one here. A galvanic cell consists of magnesium and silver. Okay, so in this case, we're going to calculate the cell potential here, and I'm going to use the subtraction version. So cathode minus anode. So really, in this case, we weren't given any overall equation. So we would go to the table, we would look up our values. And again, the one that is more positive should be our cathode, which looks like in this case, it's going to be our silver. While this guy then by default there would be our anode, or place where oxidation would occur. Since I'm going to do the subtraction, I don't have to worry about signs in this case. So I'm just going to put in the proper things there. So that's going to give me 0.8 volts minus our minus 2.37 volts. Again, that's going to really change the sign for me. So if you did change the sign, you would add them obviously together. And it looks like here that's going to be 0.8 plus 2.37. Looks like a voltage of 3.17 volts in this case. Now, if we wanted to add this together correctly, we would reverse this reaction, and that would get us, it wasn't really asked to do so, would have gave us this situation here, where the E would obviously change signs for this reaction written. We would leave the silver the way it is, but we do actually need to multiply by 2 to get the proper number of electrons. And once again, multiplying by that 2 will not affect the E value of 0.8 volts in this case. Putting these together, electrons would cancel, gives us our balanced net ionic equation that's really going on here. Silver goes to magnesium and 2 of the silvers here. And once again here, if you did that, you flip the sign, you could just add those together, you get the same cell voltage. Any questions on that there? So let's talk a little bit about cell potential and work and free energy. So a very sort of common tie-in to sort of galvanic cells is our free energy, and where is that sort of driving force that will pull those electrons across the wire. And really, again, those electrons can do some type of work as they're out there based on that potential difference between really the cathode and the anode side. And basically, the maximum amount of work that can be done is equal to really the free energy. And remember, free energy is really the energy available to do some type of work. So when we do produce a current and a cell potential is positive, by the way, positive voltage is good. Yeah, usually means it's kind of working correctly. Negative voltage, not so good. Things really don't get done in that case because you don't really have a positive cell voltage. So the relationship between our E of our cell and our favorite delta G, which is our Gibbs free energy, can be seen here. And let's talk about a couple of these equations. First off here, this one is an important equation. That is our delta G naught. It's equal to minus N. N is the number of moles of electrons. Now, when we look at the half reactions, for example, if we had somebody that was giving off 2 electrons and somebody that was gaining 2 electrons in the other half reaction, N in this case is 2, it is not 4, so don't add them together. It is the total number of electrons somebody loses, which is the same number of electrons that somebody gains. So once you get your electrons balanced in each half reaction, it is basically just the electrons from one half reaction, which is what N is. F is our friend Faraday's constant, which is 96,500, 96,487 if you like, joules per volt per mole. And remember, a joule over a volt is a coulomb, which is sometimes the unit of electrical charge that's used over a mole. That is a constant. That is a value that you kind of always have available to you. And then obviously our E of our cell is the same thing that we've been talking about, however you want to calculate it. But again, cathode minus anode is how we get to our E of our cell. Substituting that in with our delta G that we also saw in a previous chapter there with our minus NFE gives us this equation here. And at 25 degrees Celsius, a lot of these constants sort of reduce down to either one of these versions if you really want a reduced down version of it. R is the gas constant, and it is the one with energy, so that's the 8.314 version. T is our temperature in Kelvin. N is our number of moles of electrons. F is our Faraday's constant, and K is our good friend, the equilibrium constant. So this relates the E of the cell to the equilibrium constant. And again, if you want to use a sort of reduced down version, that is the natural log version, 0.0257 volts over N. And that is the base 10 there, log version, 0.0592 over N. This is our triangle of thermodynamics fun here. So if we know the E of the cell, we could get to the delta G or the K through these equations. Just like obviously if we know delta G, we can get to the K through this equation we saw earlier. And then obviously all the way around the triangle there, we could calculate for a bunch of things. So this equation is sort of important. This is why we will have a positive voltage is good, because if my cell voltage here is positive, the only other thing that would be everything else there is positive as well, which means that should give me a negative delta G. Negative delta G means spontaneous reaction, right? So we'll be going to the product side, we'll be making electrons, and this cell will work. If we had a cell voltage that's negative, the negative from the cell voltage and the negative here will turn our delta G into a positive value. And positive means non-spontaneous, right? Reactance basically happening. This cell is not going to do much for you because of that, basically. Thermodynamically, it does not going to work or be spontaneous. And that's what we see here when we compare that. Also, when we compare K. So all these things do go together. Obviously, if we have a large value of K, we will have a positive E and a negative G, right? And if we have a small value of K, that means we will have a negative E and a positive G, which means we will not get much sort of produced. Any questions on that there? Yeah. K is the equilibrium constant, so the same one that we've been using, so products over reactants, yeah. Other questions? All right, so let's try one here. Calculate the delta G for this reaction, and is it spontaneous here? Look, so in this case, we're looking for our delta G naught. We got some SRP values given to us, so perhaps this would be the good one to use. In this case, we do want to maybe figure out what's going on, so we can calculate our E of our cell, which again should be our E of our cathode minus our E of our anode. In this particular case, they do give us an overall reaction, so probably should take a peek at it to make sure. This guy here, copper, is a +2, iron here is 0. Copper on this side is 0, and the iron here is +2. So when we look at copper here, it is going from +2 to 0, which means it is actually being reduced in this case, right? So that is our reduction. The iron here is going from 0 to +2, which means it is becoming more positive or going through oxidation. So if you just went by positive here, you lucked out. It might not always be the case. So you should look at the equation to make sure. So now that we got that, we also know we could see that we do have really a balanced number of electrons here. So N will equal 2. Again, it's not 4, so it's just the 2 electrons in this case. And I think that should be everything we need. So we'll do our E of the cell here. We'll do our cathode, which is our copper in this case, 0.34 volts. Again, I'm going to be subtracting, so I'm not going to change any signs. If you change the signs, then you should be adding at this point. So if we do that, that would be 0.34 minus a minus, which becomes a plus, I believe, 0.78 volts. Now we can calculate our delta G. It will equal our minus 2 moles, our Faraday's constant, 96,500 joules per volt per mole, and our E of our cell, which is 0.78 volts. Volts will cancel, moles will cancel. Going to leave us as joules in terms of our units here. And we'll take that times A2 times the 96,500. Going to give us a delta G of minus 150,540 joules, or roughly minus 151 kilojoules. Is this reaction spontaneous? This reaction is spontaneous. I got me a negative delta G. By the way, I know it was spontaneous just by seeing the positive voltage here, by the way. You don't really need to go any further, except that we had to calculate delta G in this case. But the positive voltage tells us it will be spontaneous, because that should always lead to a negative delta G in this case. Just like if you got a negative voltage, it should be non-spontaneous, because that should lead to a positive delta G and not being thermodynamically going to be spontaneous. Any questions on that stuff there? All right, we'll lay it up there for today.